Hello everyone, today we're going to talk about the Curse of Dimensionality. The prerequisites for this material are discrete random variables, marginal and conditional distributions, independence, and conditional independence. Let's start with an example. This is an example that we already used to explain joint PMFs and also marginal and conditional PMFs. We basically were interested in modeling whether it was raining in 3 weather stations, all of them in Oregon, Coos Bay, Corvallis, and John Day. And our data consists of observations where we see whether it's raining in those stations at the same time or not. So here in our observations, 7,253 times it was not raining at any of those stations, 69 times it was raining in all of the stations, and so on and so forth. And then when we want to estimate the joint PMF between these variables, what we do is we normalize, and we get our joint PMF. The thing is that life is not an example that we see in a class. In the real world, we often are interested in the interactions between many more variables than just 3. In particular, the dataset that I extracted this data from has 134 stations over all of the United States. So now we could do, you might say, so what? What's the big deal? What you explained to us for the joint probability mass function, how to estimate it, you can just go and do it with the 134 stations and compute your joint PMF, and that's it. We'll be fine. Okay, so then let's see if we're going to be fine. How many times do you think, when I look at the possible patterns and realize that we're only caring about whether it rains or not? Okay, so we're looking at whether it rains or not in each of the 134 stations. So I can call that like a precipitation pattern, let's say. Like it rains here, it doesn't rain here, it rains here, and so on. When I look at these patterns in my data, how often do you think I'm going to see them repeated? Like I look at a particular pattern and I say, oh, how many times does this appear in my data? That's important because that's what I'm going to average to find the empirical probability of that pattern. Okay, so when I go to my data, I realize that essentially 90% of the patterns are unique. I see them once. And then about 7% I see them twice, 2% I see them 3 times, and only around 2% of the patterns do I see repeated more than 4 times or more. So if I'm going to average the times I see each pattern in order to find its probability, this is not going to work very well. In fact, if I were to observe new patterns, it is quite likely that I would observe patterns that I have never seen before, so I would have assigned them 0 probability under this empirical joint PMF estimation. And that is highly problematic, right? Because I am not able to predict the probability of future patterns that are going to appear for sure. Like if I'm seeing 90% unique patterns, I can assure you that if I look at more data, like for example from the year after, I'm going to keep seeing unique patterns. So then here we have to kind of take a step back and think, why are we seeing so many unique patterns? Maybe we should worry about how many possibilities are there. So what are the number of possible patterns? And remember that we're in a very simplified scenario where we're only looking at whether it rains or not at each station, and we have 134 stations. So yeah, the number of possible precipitation patterns is 2 to the 134, which is more than 10 to the 40. These are the entries of the joint PMF. So even if we had like all the computers in the world, we wouldn't be able to even store the joint PMF, which should give us some pause, right? Because I was telling you, just a video or 2 ago, don't worry, compute the joint PMF, and now you can compute whatever probability you want about your random variables, which represent the uncertain quantities that you're modeling, and life is great. Well, in practice, that is completely impossible. It is going to be impossible in general to compute to approximate the joint PMF of more than, like 10 random variables, and 10 is probably already pushing it because most random variables are not going to be binary, right? By binary, I mean 2 possible values. In comparison, we have 8,700 data points, so now we start understanding why we just keep seeing unique patterns, right? Our data are very, very, very few. And it's kind of funny because when you look at applications of data science or machine learning, people are like, big data, we have so much data, we don't know what to do with so much data. But the thing is that if you have a lot of variables in your model, you will never have enough data. Never. Otherwise, you could just estimate joint PMFs and do whatever you want. The thing is that we can't. And that, in fact, is the motivation for most machine learning techniques that you will encounter. Machine learning techniques try to get around this problem, which is that you cannot estimate joint PMFs or when there's more than just a few variables, because the dependencies essentially explode exponentially, like we saw in this example. And this phenomenon that we are constantly running against when we try to do data analysis is called the curse of dimensionality. Why is it called the curse of dimensionality? You can think of the variables as entries of a vector that you're trying to model. When the dimension of that vector, the number of variables that you're taking into account, grows, the dependencies explode, which means that you cannot estimate the joint PMF anymore unless you make very aggressive assumptions to simplify your model. For example, in this case, I could be like, okay, let me just assume independence. If I assume independence, then the joint PMF factorizes into the marginal PMFs, and each marginal PMF has a single parameter that tells you what's the probability that it rains at that station or not. Okay, so now I would have 134 parameters. I have 8,000 data points. In fact, I have 8,000 data points at each station, so I'm going to get a really good estimate. Then I would just compare the PMFs. What is the downside of that approach? The downside is that I wouldn't be, or actually, I should have asked you before, how many parameters do you have to estimate if you assume complete independence? And as I just gave away, it's just 134 as opposed to more than 10 to the 40. The problem, what is the problem with assuming independence? The problem is that you're ignoring the dependencies between the stations, and you might be interested in them, and there might be strong dependencies that you do want to model. Sometimes a trade-off between these two extremes is to use conditional dependence. So in the previous video, when we're talking about these 3 stations in Oregon, there were 2 of them, Coos Bay and Corvallis, that were much more related. So you might want to include that in your model, but maybe not the dependence on the 3rd station once you condition on one of those. Okay, and then it becomes an art, right, to decide what conditional independence assumptions to include in your model. Motivated by that, in the rest of the video, we're going to present a machine learning technique that does essentially this. Okay, it runs into the curse of dimensionality and it says, okay, let's assume some conditional independence and let's see what happens. Okay, so in order to motivate that machine learning technique, we're going to talk about classification. In classification, you have data points that I am denoting here by x1, x2 to xn that are annotated. Okay, the annotations here are y1, y2, yn, and you can think of y1, y2, yn as the class of x1, x2, xn. So maybe x would be some pixels, so a picture, and you need to assign a class to the picture, like is it a dog, is it a cat? Or maybe the xi's would be text from an email, and you want to classify whether it's spam or it's actually a useful email. Classification arises in many, many applications. And our goal is to assign a class to new data. Okay, so you have like some examples like this, and now you have a new x. How do you assign the new class to, how do you assign, a class to this new data? You have a new email, is it spam or not? You have a new picture, is it a dog or is it your cousin, and so on. Okay, so a reasonable approach to classification is to do some probabilistic modeling where you say, okay, these data vectors that I observe, x, are samples or realizations from a random vector, and there's an associated random variable y that is the class, and I want to understand the dependency between them. In particular, if I have a new data vector x, a reasonable way to assign the class y is to say, okay, if these guys have this joint distribution, what is the class that is more likely given that particular x that I have just observed? If we just apply, well, this is like applying Bayes rule. We just or the definition of conditional probability. If we want to frame it in terms of the joint distribution, basically you would see the joint PMF of x and y, where x is the observed data point, and then you would have to normalize. Okay, this is like when we were computing conditional PMFs for a fixed value, and here the fixed value is the observed value, okay, fixed value of one of the variables. So let's see how this works out in an example. We're going to go back to our data on voting patterns of politicians, and we're going to try to predict whether a politician is Republican or Democrat based on their voting record. For that, we're going to have 425 politicians to train with, and then we're going to test our method on 10 new politicians. Here, we're going to model affiliation as a Bernoulli random variable, which is 1 if it's a Republican and 0 if it's a Democrat. And the votes, I don't know if you remember, but basically we had these issues. One of them was budget. The other one, actually I've also forgotten, something about arms. Like there were several issues. And a total of 16, in fact. So those are the data that we're going to use to classify the politicians. If they voted yes on the issue, we assign a 1. If they voted no, we assign a 0. And now, a new politician, we're going to see a sequence of votes, and we're going to decide whether it's a Democrat, they're a Democrat or a Republican, based on that sequence of votes. It's obviously a classification problem. We want to classify between these two classes. If we want to do this through probabilistic estimation, we can try to, well, actually there's a small mistake here. This should be y given x, right? So we want to determine the probability of y given the observed data x. So, and this always happens to me. Okay, what are the possible values of x, right? Because if we have like a new politician coming in, we're going to see a voting pattern. We better have a probability assigned to every possible voting pattern so that we can actually apply this approach. So how many voting patterns are there? So there's 16 votes, 2 outcomes for each vote, 2 to the 16, 65,000. So we have a problem here, right? Because our training set only includes, let me remind you, 425 politicians. So from 425 data points, it's going to be a bit complicated to estimate 65,536 conditional probabilities that we need, because we might encounter one of these voting patterns as they come in. You might think that some of these voting patterns might be impossible, and you would be right. But as we saw in the case of the precipitation data set, you're also going to get unique unique voting patterns coming in just because there are so many of this and we have so few data. It's just the curse of dimensionality that comes to haunt us. Well, I didn't need to run back. The number of training data points was right there. So this is very problematic. Like, what do we do? Well, IfBase, which is this machine learning technique that we're going to use to exemplify ways of addressing the curse of dimensionality, IfBase says the following: assume conditional independence naively. Realize that you cannot assume just complete independence, because if you assume that y is independent with everything, then what are we doing here, right? You're just going to assign Republican or Democrat based on what you expect the fraction of Democrats or Republicans is, so you're not even going to be using the vote, so we cannot just apply independence completely. But we can, apply almost that, like apply conditional independence, which means that we assume that the votes are conditionally independent of each other given the affiliation. So we assume that for each individual vote, it only depends on whether the candidate is Republican or Democrat, not on whether they have voted in a particular way for other issues, which we know is not true, right? Because being a Republican or a Democrat is not the only reason why people vote like they do in Congress. They might, come from a certain state, like they might hold some religious beliefs, like who knows, right? Like there's many reasons why people will vote in different ways. It does not only reduce to being either a Republican or a Democrat, and you're going to see interactions between different issues. And in fact, we already saw that there are when we were talking about conditional independence of events. But IfBase, and that's why it's called naive, says, sure, All of that is very interesting, but at the end of the day, I have a job to do. I have to produce a prediction. If I try to mold the full joint PMF, I'm dead. Like there's no way, like I wouldn't, in most cases, I wouldn't be able to store it. So, shut up, let me apply my conditional independence assumption. I'm going to get a tractable model and let's see what happens. Okay, so what happens when we assume this conditional independence? Well, what happens is that when we compute the conditional, okay, just by using the definition of conditional PMF, now we can split this conditional using the chain rule. Again, we're going to split it by saying that, actually maybe I should do this a little bit more carefully. So we have P of X, Y, XY. And now what I'm going to do is I'm going to apply the chain rule, and I'm going to take Y out first, and then I'm going to take the first entry. So this is the first entry of X conditioned on Y. Now when I take out the other terms, this is where the curse of dimensionality kills me, because now here I would have to do x2 given x1 and y. Then I would have to do x3 given x1, x2, and y. Then I would have to do x4 given x1, x2, x3, and y, and so on and so forth. So the number of conditional, like the number of terms I need to plug in there is going to explode, right? Because these conditional probabilities, remember that when we condition on something, we're going to have to estimate x2 as x2 given all the possible values of y and x2. Well, okay, this is not x2, this is x1, so that's why I was getting confused. Sorry about that. So let me repeat that. We're going to have to estimate the conditional probability of x2 given all the possible values of y and x1. When we get to like x5 given all the possible values of x1, x2, x3, x4, and y, that just explodes. We don't have enough data to estimate all of that. So what we say is, okay, calm down, forget about this. Let's forget about this. Let's just assume conditional independence. And now we can plug in here just P of x2 given y. Okay, and then we're going to plug in P of x3 given y, P of x4 given y, because given y, we assume everything is independent, so this thing just factorizes. We only need the conditionals of each entry given y, and that's it, not on the entries given each other. We also, of course, need the marginal PMF of y. Okay, so I hope that made sense. So now how many parameters do we need to estimate? Remember that before the parameters were like 65,000 or something. If we use the full joint PMF, if we're only interested in these conditionals given the affiliation, how many parameters do we need? Well, we need, first of all, we need this guy, which is the probability of affiliation. So that's one parameter, probability of Republican, and then Democrat is just 1 minus probability of Republican. And then we need the probability of voting yes or no given Republican and given Democrat. And there's going to be one parameter for each, right? Probability of voting yes on the first issue given that you're a Republican, and probability of voting yes on that first issue given that you're a Democrat. Okay, those are two free parameters. So we're going to have 2 parameters per issue. We have 16 issues, that's 32 parameters, plus 1 to estimate the probability of being Republican Democrat. That's just 33 parameters, and we have 425 data points, so we might be okay. So if we do that, we just compute this and we take the maximum, we get 9 out of 10 representatives correct. So actually, in this case, the method does very well, and I was curious about the representative that is wrong, and I looked at them, and here also this gives me an opportunity to show you the parameters that we're actually estimating. So here, for the first issue, we have that 19% of Republicans voted yes, 61% of Democrats voted yes, and our error guy voted yes. So here, here they voted more consistently with Democrats. So it might look like a mistake from that point of view, but then you start looking at here, for example, very few Democrats voted yes, but this person voted yes. Here, again, very few Democrats voted yes, this person voted yes. And you can see many more examples. Like, I mean, I don't know. Here also, here. Okay, so in general, basically, if you look at this, you realize that what the algorithm is doing is basically looking for individual consistency across the votes, and it uses these conditional probabilities to aggregate them and produce a single estimate of what it thinks that it's more likely. It's making conditional assumptions that are not true, but at least it manages to produce an estimate, which doesn't mean, that you should not perhaps work harder and model some of the dependencies between these issues, but at least it gives you a pretty reasonable baseline to compare against. And this is very common in machine learning, right? Like you assume independence or conditional independence because you need to do something, otherwise you're never going to be able to characterize the joint distribution of the object that you're interested in. And this gets much worse when you have images or videos or audio, which have like immensely high dimensionalities. You say, okay, I'm going to just have to assume independence or conditional independence of a lot of things, and let's see how I do. And in order to develop new methods, often what you do is you think about how to cleverly incorporate some dependencies that might be important. Okay, so what have we learned? When estimating a joint PMF of multiple variables, the curse of dimensionality is going to haunt us very, very quickly, unless we have very, very few random variables. And the solution, or a partial solution, can be to enforce conditional independence assumptions, even if we know that they would not hold exactly. And we have provided an example of this through the IfBase classifier. Thank you very much.